0.1, right? Okay. So this thing, right, it's roughly going to be 10 angle pi over 2, 3 angle 0. This thing's pretty much just 100. This thing's pretty much just 0.1. And so then we go through and do some multiplying, and we get 30/100ths angle what? Pi over 2 minus 0.1. And that is just 3/10 angle. And at this point, you would end up calculating it because pi over 2 and 0.1 don't play nice. So you end up getting this. Okay, right? Okay, so then what is VLS1 of t? Yeah. What's omega? Yeah. Okay, did we do that right? Pi? Yeah, okay, cool. Okay, so that's the left source. Okay, we're going to do the right one really fast, because I just want to point out one thing that comes up algebraically. That came from the sum of the squares of A and B, right? So it's the sum of 100 squared plus 10 squared, yeah. Okay. So now we do the other circuit. Messily. Okay, so this is 100, right? What's this guy going to be now? So this is omega. So what's this source turn into, first of all? Yeah. Okay, and we'll just say omega equals 100 here, right? So for bookkeeping reasons. So what's ZC going to be? Let's see. In this case, it's negative 1 over, 1 over j, 100, 10 to the 6th, 10 to the minus 6. It's 10 to the 4th j, minus. Okay, that's C. And then L is just what? 100J. Okay, piece of cake. All right, so let's say this time we want to find, same thing, right? This time we want to find VLS2. What's VLS2? Left over the sum. Is voltage divider you're saying?
Yeah.
Almost. So this is, 100J minus 10 to the 4th J. Okay, so 100J over 100J. Okay, sorry. I need to leave myself more room. Yeah, Z left is, that's Z left. Okay, Z left over Z left plus 100J. Okay, that's not everything yet, though. I think that's the first time I've ever done that thing where the zeros do that. So you guys saw it. Yeah.
Just to go back.
Yeah, sure. I'm speeding through, so yeah.
So you tossed out that 10J because you called it insignificant.
Where?
Where you wrote Z right equals some stuff.
Yeah, here?
No, up top board. There you go.
Top board, yeah.
Yeah, to the left, you wrote Z right equals.
Yeah, that 10J minus 10 to the 5th J,
You said it's insignificant.
it's very small.
What's the point at which?
Well, the point at which something is insignificant depends on your tolerance, right? So in this case, the difference is between it being 100,000 or 99,990, right? So that's pretty close, I guess, is the difference, right? So 10 to the 5th, right, is 100,000. 10 to the 3s, well, 10 to the 3 is getting a little dicey. Maybe it still will be okay, right? But I'm just saying, right? I mean, I just arbitrarily decided I don't care about 10 to the 4, if that's the difference, right? So I'm just saying you can approximate it by that. If you want, you can find the exact amount by which it'll be off. And what you'll find is that it's going to be like 0.01% off, right? So I'm just saying, with some experience, you'll realize that 10 to the fourth is a pretty big difference. So yeah. And that things like the capacitance tolerances or like your voltage noise and your voltage source would just dominate.
If you weren't going to throw it out, then what would it look like?
Oh, I see. Well, in that case, right, it would just be, you'd end up with a different expression for, I mean, you would just write out, instead of writing 10 to the fifth j there, you would write 99,990 j, and then get a different answer, right? So instead of getting 10j, you'd get like 10.121. You need a calculator. That's kind of the answer, right? I didn't want to use a calculator much.
Well, I mean, would you just keep it like 10j minus whatever on the bottom?
No, you would write it as an actual whole number, right? At that point, you'd write it as 99990j, and that would be that's the number you're now carrying around. That's magic. Yeah. Okay, cool. So here, so we're not done, right? We want VLS2. What's it going to be? Times 5 angle 0. Yeah, okay. That's not everything though, right? So what does this quantity tell us? So I'll give you another thing. Let's call this V hat X. Okay. Are V hat X and VLS2 the same number? No, right? You see why, Dan? This is V hat X. This is VLS2. Sorry, VLS2 is the voltage across them, right? So what's the difference? Why are Vx and VLS2 different? Because the other side's not ground, right? Yeah, okay. So VLS2 is what? It's this. This right here is Vx, as I've drawn it. So what do we need to do here? Yeah, minus 5 angle 0. Okay. So the branch voltage is the difference between the node voltages, if you'd like. Okay, so without belaboring the point too much, we can do a similar set of approximations and stuff. And what we'll end up getting in pretty quick order is that Z left is about 100. Okay, and the reason is you have two things in parallel. You have 10 squared and minus 10 to the fourth j. The 100 is pretty much going to dominate the expression when you do it, and ends up just coming out of the 100. So, you know, I invite you to try it, but it's not hard, and you just do some algebra, and you find that, okay, it's 100. So there's kind of this general rule that will come in very handy when you're doing these circuits, which is that two things in parallel are dominated by the one with a small magnitude. You don't have to know that, but it'll save you a lot of work doing algebra. And, you know, I guess on a midterm I would say something like, if the difference is 10 to the fourth, you may ignore and do the parallel much faster, right? Okay, so you find Z left is 100. And so that basically just means that VLS2 is 100, or sorry, okay. Yes. Pardon? Z left is this box, that whole left side, because we were doing this voltage divider thing. So hopefully you can see that whole left side voltage divider style. I'll give you this. So this is 5 minus 5. Okay, so if we want to combine this all into one big expression, what will we need to do?